Hi, this is Professor David Farina. In today's lecture, we are going to be discussing light and matter, and specifically its connection to the inner workings of our cosmos. In today's lecture, we're also going to be discussing waves and wave interactions. Let's get started. There are two main types of wave. The two main types of wave are mechanical waves and electromagnetic waves. And that's about where the differences and similarities end. We've got both of these are waves, and they both transmit energy, and they both do not transmit matter, but pretty much everything else is different. In a mechanical wave, we have that these waves require a material, a medium to pass through, matter. With an electromagnetic wave, we do not require a medium. The vacuum of space is easily passed through by an electromagnetic wave. However, a mechanical wave like a sound wave could not pass through the vacuum of space at all. So the electromagnetic wave is much different, and it comes in many different types. We've got the mechanical waves coming in longitudinal, compressional, and transverse types of waves. And an electromagnetic wave is just a transverse wave. And we'll get into a little more detail with this later on. So, when we're talking about waves, we need to understand some of the terminology that's used. One of the important pieces of terminology is the amplitude of the wave. The amplitude is kind of like the height of the wave. If you think about it like a wave you'd see in the ocean. The high amplitude wave would be this blue wave at the very top. A medium amplitude wave would be like the green wave here. And the low amplitude wave would be like the red one right here. You'll notice that each of these waves have the same wavelength and therefore the same frequency, which we'll discuss in just a moment. The only difference between these waves are their amplitudes. Now, the amplitude can be measured as a distance, and it's the distance from this resting position, this solid line that goes across the bottom, to the maximum height of the crest or the minimum height of what's known as the trough. We have a crest and a trough for every wave. So we have crest, then trough, and then crest, and then trough. So each of these, this would be two whole waves. How many waves would be here in this top diagram? Pause the video and count for yourself. All right, now that you've had a chance to count, let's count together. We've got one wave. We've got two waves. We've got three waves, 4, 5, 6, and we've got 7 waves. So learning to count waves is pretty simple. All you have to do is for every crest and trough, you have a whole wave or one wavelength. Now the wavelength is a measurement from crest to crest of the wave. And this affects directly the frequency. So wavelength is the distance between two identical points along the wave. You could even also go to the trough, so from trough to trough, or from this point here to this point here. It doesn't matter where you measure from, so long as you're being consistent. You'll see that the wavelength on this top wave is a little bit longer. We have a medium wavelength for this green one in the middle, and then we have the shortest wavelength on this blue one on the bottom. Now, this can also be translated into the frequency, the number of waves that repeat themselves over a given time period or time interval. So this is represented as something called hertz. A hertz is how many cycles per second. Now, you may be familiar with hertz when we're talking about something like a radio station. So with the AM stations, these are all in kilohertz. And for all FM radio stations, these are all in megahertz. So favorite radio station If you think about that, most of them are FM radio waves. At this point, you're talking about a number in megahertz, and so that's what we're seeing on our radio station. So the speed of a wave can be found if you know both the frequency and the wavelength of a wave. For our purposes, we're going to be discussing electromagnetic waves, so the speed is known to be the speed of light. However, the speed of light does change if it is passing through a medium, so be careful to always assume that the speed of light is the same. The speed of light that you are probably familiar with is the one that's when it's in a vacuum. And when it goes and enters into a material, it does in fact slow down. So we could actually measure the wavelength and the frequency of a wave and then determine the speed at which light can pass through a given medium. Wave motion is mostly this up and down motion as we've been discussing, but what a lot of people don't realize is that this wave motion does not transport actual material, actual matter. It's just the transportation of energy. Next time you're at the beach and you're floating in the ocean and a wave passes by, it'll be pretty evident to you that the wave, unless you're trying to catch the wave, which is different, if you're just kind of hanging out there, the wave will pass right through you and out the other side, and you will not be carried along with the wave unless you're attempting to move with it. You kind of bob up and then come back down again, but you won't actually move with the wave. Diffraction is also a property of waves. When we have an interaction with, let's use the example of a water wave. Here we have a breakwater. So maybe you have some sandy beaches back here that you want to protect. The ocean waves are coming in and they hit this barrier. They can be deflected or bent as they hit this breakwater. Now, diffraction can happen with light as well, and oftentimes is an anomaly or an effect that happens as a result of our optics. So when we get into our discussions on telescope designs, we'll be discussing a little bit more about diffraction and also how something can be diffraction limited when we're talking about telescopes. We also have something called constructive interference. So constructive interference is when we have two waves that are combining to form a bigger wave. So we've got a red here and the blue, and the red and blue combined make the green. Notice it's taller. We also have the two troughs coming together, and we combine to make a bigger trough. So constructive, you're adding together the wave's height, the amplitude, and we are getting a bigger result. The opposite of this is destructive interference. So we've got, once again, our red. Notice they are opposite directions now. Red is at a crest phase, blue is in the trough phase, and when we put the crest plus trough together, they're the same amplitude, but in opposite directions. We end up with the green resulting line, which is a flat line. So no wave anymore. It's been destroyed. Whereas we have the opposite here. Now notice we've got a situation where we've got the red being a little bit smaller, blue being a little bit bigger, and the resultant wave is a smaller wave than the blue wave because the red wave has destroyed some of that energy. But notice it is still in the downward direction because the bigger of the two waves over here, the blue wave, was in the downward direction. So that's destructive interference. So I hope you enjoyed the lecture today on waves and wave interactions. Hopefully it was helpful for you. And hit like and subscribe at the bottom to learn more.